Hello everyone, welcome to the course Manufacturing Processes. I am Kishore, presently working as Assistant Professor in the Department of Mechanical Engineering, MLR Institute of Technology, Hyderabad. So, last class we discussed about design of a sprue and pouring time. So, in detail we discussed about that, and also we took some numericals based on these two concepts to further go inside these concepts. Today in our presentation it will be importance of riser and riser design. We will start with the basic and we will see why riser is important in gating system and what are the important aspects that need to be considered during the design of the riser. So, we will start with the riser. So, this is the diagram for the gating system. You can see this is pouring basin. So, we will pour the metal here and through a sprue it will come down, and this is the runner section, and it will go inside the mold cavity. On the top of this riser is there. This is top riser. So, metal will come inside and also go up from this mold cavity to this riser. So, now what is the importance of riser? Why do we need riser? So, at the starting lecture when we started this gating system, we have already discussed the gating system is nothing but it's a reservoir for molten metal. What happens whenever the material change its state, whether it is from liquid to solid or it is gaseous state to liquid or liquid to solid, always there will be contraction in the volume. Similarly, if we are heating the material and it is changing its phase from solid to liquid and liquid to gas, we know that there will be expansion in the volume or expansion in the material. So, what happens when we pour the metal, it will go inside the mold cavity, and in that state metal will be in liquid state. So, after some time it will solidify over there, and as it is solidifying, so state is changing from liquid to solid. So, definitely there will be contraction in the volume of the material. So, what will happen, whatever the shape of the cavity was, suppose my intention was to produce a particular shape or size of a product, because of the contraction that dimension will reduce. To compensate that, this riser is used. Now, what is the basic requirement? What should be there in the designing so that our requirement will be fulfilled by the riser? So, there are two parameters during the design of the riser. These are the basic requirement of a riser design that we need to be considered. The first parameter is the molten metal inside the riser. This is the riser. So, whatever the molten metal is over there, it should solidify after the solidification of the mold cavity. Why I am telling this? Suppose we have to fill whatever the contraction has occurred because of the solidification in this mold cavity, and we want to compensate that, we want to fill that, or we want to fill that particular gap because of the shrinkage over there. So, it is important to understand that liquid should be in molten stage in this riser. If it is not in molten stage over there, so what will happen? Suppose it has in solid form in this riser, and this one already contraction is there. So, this solid anyway is not going to fill the shrinkage part in the mold cavity. So, it is very important to understand that the material or the metal which is there in the riser can only fill the mold cavity shrinkage whatever has happened over there in the mold cavity when it is in liquid state. If it is not liquid state, definitely it is not going to fill over there. So, first requirement of this riser or the basic requirement of this riser design is we will have to make sure from our designing that the riser should solidify after the solidification of the mold cavity. This is the first requirement. Means if we write in terms of this one, if I am writing T, solidification time for riser, so this should be greater than the solidification time for the mold cavity, that is the C. It is very important to understand this. Okay, this is the condition. In that particular condition, liquid will be in metal will be in liquid state in the riser, and easily it will come and fill the mold cavity whatever the shrinkage has happened over there. Second condition is how much amount should be there in the mold riser so that metal will come and fill the mold cavity. So, it is obvious, easily we can understand whatever the shrinkage has occurred over there, whatever the volume contraction has occurred in the mold cavity, that we need to fill. So the volume of metal over there in the riser should be sufficient to fill the shrinkage occurred or volume shrinkage occurred in the mold cavity. That is the second basic requirement of the riser, that the volume of the riser should be greater than the volume of the shrinkage volume. So these are the two conditions that need to be fulfilled. Now, how much it should be greater? If question will come in the mind. If I am telling the volume of the riser should be greater than the volume of the shrinkage volume. If I am taking this volume of the riser VR and I am telling this should be greater than the Vs. Now the question will come, how much it should be greater? So generally it is taken as 3 to 5 times. 3 to 5 times of shrinkage volume, that is Vs. And this is the general practice. Generally it is being taken, okay, 3 to 5 times. So if we will write this one, the shape side we are taking 4, so we can write the volume of the riser should be greater than 4 times of the volume of the shrinkage. This is the general practice. Shape side it is being taken as. So if the volume or the metal volume, molten metal volume over there in the riser volume is greater than the 4th time almost of the volume of the shrinkage, then safely we can say that whatever the shrinkage has occurred over there in the mold cavity can be easily filled by the riser. So these are the two basic requirements of riser design that need to be considered at the time of designing of the riser. To understand this two basic principle, I have taken one numerical. Through that we will further understand how to go inside this basic principle of the riser design. So this is the numerical. This is a gate numerical, previous year gate numerical. So this is a conceptual numerical. That is the reason I have taken here to make the concept, the basic concept of the riser design clear. So what this numerical is: an aluminum cube of volume of 10 centimeter side has to cast with the cylindrical riser of height equal to its diameter. So riser is of cylindrical shape. This is a cylindrical shape riser, and suppose its height is h we are taking. So this height is h given, and also this diameter is, suppose we are taking a small d, so it is given in the problem d is equal to h. That is given in the problem, equal to the diameter. The riser is not insulated on any surface, means all the surfaces are free for transference of heat. Okay, if the volume shrinkage of the aluminum during the solidification is 6%, if the volume shrinkage of aluminum during solidification is 6%, then find the shrinkage volume. This is 6% of actually this mold volume. Okay, na? So of this. Okay, so find the shrinkage volume. So first we have to find out the shrinkage volume, means we have to find out the Vs. Our first requirement is to find out the Vs. So how to find out this Vs? Clearly in the problem it has been told that the shrinkage is of 6%. Okay, so if we are calculating this Vs, so this Vs is given as it is 6% of volume of the mold, that is Vm or Vc, whatever we will write. So we can calculate from here what will be the volume of the cavity or volume of the mold. If we are writing Vc or Vm for the mold cavity, so we know it will be, it is a cube shape, so it will be cube of this one. So this will be 1000 centimeter cube. So volume of the cavity is 1000 centimeter cube. So if we are taking this one, 6% of this one, so this will be 1000 into 6 upon 100. So this will be cancelled out. So finally it will be 60 centimeter cube. So this first part answer will be, what will be the shrinkage volume? It will be simply 60 centimeter cube. So this is the volume which has been, this is the shrinkage volume in the cavity that we need to fill. So what we'll have to do, we'll have to design this cylindrical riser. This has been given in the problem. This cylindrical riser will fill this shrinkage volume. So now in second part we have to find out what is the minimum size of the riser in the terms of diameter, that we will find out. So what we have seen here, in the previous slide, that the volume of the riser should be greater than equal to approximately 4 times of the volume of the shrinkage. So this volume shrinkage already we have calculated, and what will be the volume of the riser we can find out. So if you apply the formula, so we can write for second part, this is the first part and this is the second part. So if we are taking this first part and this one as second part, so in second part we can write what is the requirement, that volume of the riser should be greater than equal to volume of shrinkage volume. So if we are writing this one, we can write this one pi upon 4, that is volume d square into h, volume of the riser, because this is of cylindrical shape, this is greater than equal to, this should be greater than equal to, what is the volume of shrinkage, it is 60. So we can do here, we have a space. So if you are writing this h and d is given, the both are same, so we can write this one pi upon 4, sorry, this is actually 4s into 4, no, 4 times of this shrinkage volume. So pi upon 4, and for h we will write d, so it will become d cube, this should be greater than equal to this 60 into 4 means this is 240. So from here we can write d cube is greater than equal to 240 into 4 upon pi, and this is 1/3. If we calculate for d, we'll find out, we'll find this d will be equal to approximately 6.67 centimeter. So according to this one, the volume, minimum volume of the riser should be 6.67, but this is not the answer. Why this is not the answer? If you remember, I told during the design of the riser, these are the two basic parameters that we need to consider. So first parameter, second parameter we are fulfilling here, that the volume, minimum volume should be 6.6 centimeter. But what about the first parameter, that is the solidification time there in the riser should be minimum. So we will also have to check from this first criteria. If these both criteria is being satisfied simultaneously, then and only then that value will be appropriate for this particular case. So we will check for this first criteria also, and then we will come to the conclusion what will be the minimum diameter or minimum size of the risers. For that we will have to find out this solidification time. So we know the formula for the solidification time. For further lecture, of course, we will come to this one. For the time being, I am writing solidification time. If I am writing for riser, so this riser of course should be greater than equal to solidification time of the mold cavity. So I am writing C for this one. Okay, so this TR we can write a constant, we know this gamma upon volume upon surface area of riser, a square of this one, this should be greater than equal to, this will be volume upon surface area of the mold cavity, and a square of this one into this gamma, that is constant. Okay, so as material is same, we are working with aluminum, so material is same for both. So this gamma will be cancelled out from both side, this, because this is dependent upon the material and material is same, so we can cancel out this one, and this volume upon surface area. So what will be the volume of this one? We can write as pi upon 4, this is d square into h, upon the surface area will be, so two circular parts are there on the top and the bottom. So we can write, what we can write, pi upon 4 into d square into 2 plus the area of the slant part, so it will be simply pi d h we can write. Okay, small d, and this will be greater than equal to, this will be greater than equal to this volume of this one we have already calculated, it is 1000 for the mold cavity, and surface area will be 6 times into a square of 10. Okay, so finally we will calculate, we can put the value, so we can write this one will be pi upon 4, and as d and h both are equal, so this will be d cube, and at the bottom we can write pi upon 4, and this d square into 2, and this one we can write plus this pi, and this is d square. This should be greater than equal to 1000 upon 6 into this is 100. So now we have to find out. So in whole equation, if you will see in this whole section and this whole equation, only unknown is d. So if we calculate with reshuffling the equation, we will calculate the value of d. It will comes out d should be greater than equal to, this value is approximately 10 centimeter. Okay. So this is the second condition. And what was the first condition? Here was the first condition. This was the first condition. And this is the second condition. So from these two, from first we are getting that diameter should be greater than equal to 6.6 centimeter, and from the second condition we are getting that diameter should be greater than equal to 10 centimeters. What will the answer? The answer will be 10 centimeter. That is the minimum diameter required for the riser, and that is the value which will be satisfied from the both conditions. So answer will be, answer of this question will be 10 centimeter. Okay. So we will stop the lecture here, and in the next section we will come up with solidification in casting. Okay. Thank you.
Thank you.